Imagine standing in the stands, watching a cricket ball launch into the air for a massive six. If you wanted to calculate exactly where that ball is going to land, where would you even begin? You could try logging every possible detail: the specific brand of the bat, the exact shade of red of the leather, the length of the grass it might eventually bounce on, or the precise stitching pattern of the seam. But if you attempt to process all those minor variables at once, you hit a wall. The natural world is infinitely complicated. Trying to measure and calculate every single interacting atom and force simultaneously leads to total data paralysis, which poses a difficult problem. If studying the world in full, microscopic detail is physically impossible, how did we ever figure out the math behind planetary orbits or decode human biology? The answer relies on a highly counterintuitive strategy. To understand the universe, scientists don't try to measure everything. Instead, they figure out exactly what to ignore. To make sense of reality, scientists use models. In science, a model isn't a physical replica. It's a simplified way of looking at a complex system, built by intentionally stripping away any details that aren't necessary to answer a specific question. Take the Indian physicist Meghnad Saha. In the early 20th century, he wanted to understand the internal mechanics of stars. A star is a violently chaotic environment. Saha could have tried to account for every single atomic collision, or map out the wildly unpredictable chemical reactions happening every microsecond. Instead, he chose to ignore them completely. He modeled the star simply as a giant, uniform sphere of hot gas. By removing the microscopic chaos, he was able to isolate the direct relationship between the star's internal temperature and the color of light it emits. This deliberate process of simplification allows scientists to cut through secondary noise and isolate the exact signal needed to solve a problem. Once reality is stripped down to a clean model, you need a precise way to describe how the remaining pieces interact. Everyday words are too ambiguous, so scientists rely on mathematics. An equation is simply a compact statement about how specific quantities relate to each other. But for those equations to actually work, the units measuring those quantities have to mean the exact same thing, no matter who does the calculating. That's why measurements are locked into agreed-upon international standards, like the kilogram. If mass, velocity, and force aren't defined identically, the math collapses. In one famous incident, a ground crew calculated the fuel needed for a passenger flight using pounds per liter instead of kilograms. Because a kilogram is more than twice as heavy as a pound, the plane was loaded short and ran out of fuel entirely in midair. The pilots managed a terrifying emergency landing, but it proved a harsh reality. A brilliantly simple scientific model becomes a real-world catastrophe if the units aren't strictly standardized. Before committing to highly precise math, scientists frequently rely on another tool, the rough estimate. This pushes simplification to the extreme, letting you quickly check if an idea is even physically possible. For example, imagine trying to calculate the exact volume of air you breathe in a single day. You don't need highly sensitive medical equipment to get a useful answer. You can simply reason it out. Think of a standard rubber party balloon, which holds about 2 liters of air. It takes roughly 4 normal breaths to fill it, meaning one breath is about half a liter. Multiply that by 12 to 15 breaths a minute across the 1,440 minutes in a day. Run those approximate numbers, and you arrive at an enormous figure. You consume roughly 10,000 liters of air every 24 hours. That number isn't perfectly exact, but it doesn't need to be. Approximate reasoning immediately establishes the scale of a problem. It tells you right away whether a precise calculation you do later is well within the realm of possibility or wildly off base. When you combine simplified models, standardized math, and rough estimations, you get the ultimate payoff. You gain the ability to accurately predict what will happen under new conditions, often before you even perform an experiment. This predictive power is incredibly useful for testing claims. For instance, there is a persistent viral myth that any food left out during a solar eclipse becomes toxic to eat. A scientific approach strips away the superstition by asking a few basic, measurable questions. Does the temperature drop significantly? Does anything chemical react differently? What physical change actually occurs to the environment during an eclipse? The answer is nothing. An eclipse is simply the moon casting a shadow on the Earth. Because leaving food in a regular shadow doesn't magically spoil it, the entire claim rapidly collapses under basic logical scrutiny. Scientific thinking is essentially a powerful dual-purpose tool. It acts as a magnifying glass, allowing us to examine evidence closely, but it also works as a compass, helping us navigate a noisy world by knowing exactly what details to ignore.